right, so let me introduce our presenter. It's Matt Collins, the hydrologist and a geomorphologist from NOAA's Restoration Center's Northeast region. Manages a monitoring program that evaluates habitat restoration project outcomes. Matt also provides technical support for fish passage and inland restoration projects, specializing in fluvial set dynamics and flood hydroclimatology. Recent work explores climatic changes in the floodplains of Northeast U.S. rivers and associated implications for fisheries resources and restoration project design. Matt is also a repeat presenter because he does such cool stuff, and he's a nice guy. So thanks for coming back, Matt. I will leave it in your hands to go ahead and present.
Okay, great. Thanks, Kathy. I hope everyone can hear me. I guess if you can't, I won't know that immediately. But anyway, thanks for having me, and we'll just get started. So I'd like to begin by acknowledging all the people that are involved in both of the studies that I'm drawing from today. There are a lot of people doing great work on both modeling and monitoring of the Simkins dam removal, and their names are all listed here associated with the published work that we have. These two papers, by the way, have all the details of what I'll be summarizing today and more. And I'm happy to send you copies if you aren't able to access them yourself. One point to emphasize, and it's pretty important, this talk focuses on the model validation study, the first one listed. And I was not the lead author of that paper, nor was I the modeler. That was, of course, Yantao Sui. But Yantao wasn't available to give this talk, and he convinced me or assured me that I could cover it adequately. So we'll see how well I do with that. So I'd like to start with what I call a presentation map, or an outline of where I'm going with it. And you'll see it's pretty standard fare for a technical presentation. I'm going to begin with the study motivation and the objectives. I'll talk about, of course, the details of the study area, and then give a bunch of details about the methods and the results, and then wrap up with a summary of kind of the main points. So we were motivated by a relatively uncommon opportunity to validate with long-term monitoring data sediment transport model forecasts for a dam removal. There's a lot of sites with monitoring data or sites with models, but there's fewer with both. And we also could test whether more detailed input data than what the model requires improves its performance. So these are what we call hindcasts, and so making predictions after the fact. So our objectives were very simple. First, we wanted to compare forecast model predictions for bed elevations after dam removal with field measured elevations. And there were 3 simulations to validate. So we wanted to validate the forecasts. Second, we wanted to compare hindcast model predictions for bed elevations after dam removal, also with field measured elevations. So again, these were not forecasts done before the removal. These were 3 models that we developed after the fact with progressively improved input data that I'll describe shortly. So now that we know the study motivation objectives, I'd like to describe the study area. The Simkins Dam was in the Patapsco River watershed, which is shown in this LiDAR-based image on your right. It's west and southwest of Baltimore, so my cursor's over Baltimore right now. And it discharges directly to Chesapeake Bay. The Simkins Dam was about 20 river kilometers upstream from Chesapeake Bay, so my cursor is pointing to it right now. It was about 3 meters high. It stored about 70,000 cubic meters of sediment, which is mostly sand and fine gravel, and it was removed in 2010. There was a considerably larger dam less than a kilometer downstream, and I'm now pointing to the location of that one, that was removed in September 2018. And this was the Bloody Dam. At about 10 meters high, it also is filled with sediment, although a much larger quantity and with a different mix of grain sizes than Simkins. it's important to keep in mind for the rest of this talk that the Bloaty Dam was in place for the whole period of the studies that I'm describing for you today. So we're not looking at anything associated with the Bloaty Dam removal. Taking a closer look at the site, the Simkins Dam study area, both for the modeling and the monitoring, is about 15 kilometers downstream from Ellicott City, Maryland. So that's Ellicott City's here. I'm showing with my cursor in the inset map. And the study reach is this red rectangle. And that red rectangle is what you see stretched across your screen as a LiDAR map. So this study area straddles two physiographic regions. The Piedmont, upstream, that I'm circling here with my cursor, and the coastal plain downstream. And the two, the contact between the two, as you may know, is a regional feature called the fall line, and it's represented on this map as a line in purple. It's more like a zone, but nonetheless, we're representing it as a line. There's often falls where rivers cross this geologic contact because of the change in erosion resistance between Piedmont stream beds, which flow close to bedrock, and coastal plain streams, which tend to be sand-bedded with bedrock that's much deeper. Many East Coast cities, like Baltimore, developed around this feature because of the available water power. But it's important to just say that it just so happens there are no falls on the Patapsco River in the fall zone. Not every river has them, but nonetheless, there's this big change in physiography across this contact. So the Patapsco River in the Piedmont section is gravel bedded, it's comparatively steep, and it flows in a narrow and incised valley before entering the much lower gradient and sand-bedded, unconfined coastal plain section. So you can see that just on the LiDAR image. It's much more narrow, incised, and confined in the Piedmont section, and then it opens up into the coastal plain section below the fall zone. So now to the methods. To simulate sediment erosion, transport, and deposition following Simkins Dam removal, we use the one-dimensional Dam Removal Express Assessment Model 1, or DREAM-1, which is basically designed for sand. For the sediment transport capacity calculations, the model uses Brownlee's 1982 bed material equation and considers the transport of sand and coarser particles as one unit for mass conservation calculations. So, in other words, there's no particle sorting. Silt and clay-sized particles are assumed to be transported as wash load that's not able to redeposit onto the channel bed once it's released into the water column with erosion of the impoundment deposit. The model simulates erosion of the reservoir deposit by assuming a trapezoidal channel shape. So the channel widens as it degrades over time because of that feature. Downstream of the dam, the model assumes a rectangular channel shape, which can be different from node to node, but it doesn't change over time. Excuse me. I have a little bit of a cold, so now and then we may be detained by coughing.
Hey, Matt, real
so
quick. Matt, since you're at a pause point, can you, Matt's on page 9 right now of his presentation. There's a few people who are going to be following PDF as I send them. So if you could occasionally note your page number, that would be great.
Sure. Yeah.
Thank
so
you.
I'm on page 9 now of the slides, which details the input parameters and the output for DREAM. So DREAM has these primary input parameters. One is the initial channel profile, and this is a figure from our paper showing that estimated pre-dam profile. It also requires cross-sections represented by active channel widths, which we estimated from aerial photographs. And you can see that we have a comparison of those estimates in the dots with actual ground survey taken later. And we did pretty good, except for one area that I'll be describing more later. We also need daily average discharge for the simulation period. And for this, we take different sequences of actual wet, average, or dry years from a USGS gauge upstream of the site. And you'll hear more about that gauge and 2 other gauges shortly. We need initial sand deposit thicknesses in the reservoir and downstream. We need a sand supply rate and grain size distribution. Now, as I mentioned briefly, the impounded sediments were predominantly sand sized with a D50 ranging between about 0.5 and 2 millimeters. And the sand supply rate, we estimated at about 4,000 cubic meters per year. The model also needs a downstream bed surface D50 for the entire reach length of the model. So for output, the model gives you the evolution of the sand deposit thickness in the reservoir and downstream, sediment transport rates over time, and the daily average total suspended sediment concentration along the river. This presentation, I'm focusing on this first one, how bed elevations changed in the months and years after the project. There were very little finds in the impoundment deposit, so number 3 really wasn't a big factor. And we're not going to get into details of rates, which is the second bullet. So continuing methods, for our model validation, it was very straightforward. We simply compare predicted bed elevations, in other words, sediment thicknesses, at specific times with field measures values from those times. And we had, as I mentioned at the outset, 3 forecast models defined by the hydrology simulations. So 3 simulations total to validate. Run 1 was an assumed wet year followed by an average year followed by a dry year. Run 2 was average, average, wet. And then run 3 was dry, average, wet. So of course we don't know what the hydrology is going to be in advance, so we have to guess it, basically. So now I'm on slide 11. For the hindcasting, we're doing something different. We're not evaluating forecast accuracy. Instead, with hindcasting, we're evaluating model performance with progressively improved input data that in some cases we can only know after the fact. So for run 4, we take the forecast model and run it with the actual recorded discharge over the post-removal period. So this helps us assess how much our model accuracy depends on the assumed hydrology in runs 1 through 3. You'll see that we use this hindcast model as a comparison point for our forecast validations for that reason. Run 5 does the same thing. That is, it has actual recorded hydrology, but it also adds improved geometry, both field measured cross-sections taken from pre-removal monitoring surveys and actual bed elevations from the same surveys for the long profile. Instead of water surface elevations, which is what we used to model the long profile for the forecast models. And I meant to mention that a moment ago, but I didn't, so I'll clarify that again. For the input to the forecast models, we used a long profile that was from a water surface elevation survey. In our hindcast models, we're replacing that with actual bed elevations for the long profile. And we're replacing the simplified cross-sections from aerial photographs with actual field measured cross-sections. So run 6 does all of the above. It has recorded discharge, field measured channel geometry, and it adds an improved estimate of impounded sediment volume. The design engineers for the Simkins dam removal estimated the sediment volume stored behind the dam. The DREAM 1 forecast models assumed the average of the range that they presented. But our monitoring studies suggested that the actual stored sediment volume was at the lower end of that range. So run 6 uses that lower value. As with the forecast validations, with these 3 hindcast models, we compare predicted bed elevations with field measured values. Okay, so now let's just quickly review the monitoring methods. These data, after all, are the data used to evaluate the forecast and the hindcast models. So at the Simkins site, we have 3 stream gauges. Oh, by the way, I'm on slide 12. We have 3 stream gauges measuring continuous discharge. One is upstream of the site, and I'm pointing to it now in the inset map, a green dot above the red rectangle, or upstream of the red rectangle. That's a site with about 70 years of record. We also established 2 other gauges in the study area, so now I'm down on the LiDAR map pointing at 2 green dots. Those are 2 that we established for the dam removal studies. So for the DREAM-1 forecast models, runs 1 through 3, the wet, average, and dry water years were identified from the upstream gauge record, that long 70-year record. And they were applied with a drainage area adjustment at each model node. For the hindcast models, runs 4 to 6, which run actual discharge for the post-removal period. The discharges recorded at the 2 downstream gauges were used. We resurveyed cross-sections throughout the study area. These are the basic data used to evaluate the sediment transport models. They're shown here on slide 13 in black, and I'm pointing to them now just as examples. There were 26 of them. We compare erosion or deposition at a particular cross-section and survey date with what a given model run predicts at the same location for the same time. So it's pretty straightforward. We also surveyed 5 areas in greater detail where we expected substantial erosion or deposition. These were areas where we actually did full bottom topography that include the Simkins and Bloaty impoundments. So this is the Simkins impoundment that I'm tracing with my cursor on slide 14. This is the Bloaty impoundment. And there were 3 areas down near the fall zone where we had that change in gradient where we were expecting enhanced deposition. So in these areas, we used the elevation changes to compare to model predictions. We had greater detail to use, so we used it. I just want to point out, notice downstream of Simkins Dam, there's a small free-flowing section that has the gauge, and then there's the Bloaty impoundment here. That'll come up later. Okay, so finally, we can look at results, and we're going to begin with validation of the forecast models. And we're going to spend a little time on this first one because it's setting the template for all the others that follow. So just to orient you, reach 1, right here, is the Simkins impoundment and a small area upstream of it. Reach 2 is the Bloaty impoundment in that short free-flowing reach above it. Reach 3 and below, these 3 zones, is free-flowing to Chesapeake Bay. Reach 3 itself is relatively high gradient Piedmont. Reach 4 is the fall zone and the transition to the lower gradient coastal plain. And then reach 5 is just flat out coastal plain. And a bunch of reach 5 in the model is not covered by our monitoring cross sections. Our monitoring cross sections end about here. So these are results for February 20.
Matt, I'm sorry, can you say here is for those who are following the PDF?
Oh, sure. It's page 16. And I'm pointing my cursor kind of midway through reach 5. I'm pointing at the last dot, which represents the last cross-section observation. So this plot shows results for February 2011, which is about 2 to 3 months after dam removal. Shown are the 3 forecast runs with assumed hydrology. That's runs 1, 2, and 3 in the legend. And hindcast run 4 for comparison. And remember, run 4 is recorded discharge, and that's nicely said right on the plot. Also plotted other cross-section observations, which is what really occurred, and these are the dots spaced irregularly throughout the whole study reach. So you can see that the wetter forecast models, which are runs 1 and 2, in the grayish line and the dotted line, they predict more complete erosion of the Simkins impoundment than we measured in the field by February 2011. You can just see that by looking at those two curves, which overlay one another. The actual erosion at that time was considerably less. Consequently, they also predict greater deposition in Reach 2, including the bloating impoundment, than we actually measured at that time, February 2011. And you can see that just by comparing the dots with the model runs. Runs 1 and 2 also show deposition down near the fall zone in Reach 4 at this time, which we know didn't happen until about 7 months later. Observations downstream of Bloaty, reaches 3 to 5, are measuring natural erosion or deposition at this time. So runs 1 and 2 show erosion of the Simkins impoundment happening too fast by February 2011, partly because they're wetter than actual discharge, run 4, up until that time in the project. But notice that even run 4 is too complete. Run 4 is the dark black line. So it's ahead of observations as well, even with actual discharge. So greater flow doesn't totally explain why the model does this. So I'll try to explain part of the reason. So part of the reason this happens is related to the way DREAM simulates erosion. It makes all of the erodible sediment available for erosion after removal and has a progressively widening trapezoidal channel as it incisors. In real dewatered impoundments, the incised channel may only widen to accommodate the discharge magnitudes that were experienced to date. So some sediment stays in place for an extended period of time until it's accessed and mobilized by sufficiently large flows. This is what we've begun to call event-driven erosion, which is a term we use in one of the papers I listed at the beginning of the talk. And this is a phenomenon that's been observed here at the Simkins site and many others around the country. So, for example, Merrimack Village Dam in New Hampshire, or Marmot Dam in Oregon, and even the Elwha dams in Olympic National Park. So the model doesn't simulate that complexity. That's one of the reasons it's too fast. Another reason these runs show erosion happening too fast compared to observations is because, as noted earlier in the methods, the estimated quantity available for erosion in the forecast models was too high. It was about 20% too high. So we're about to leave this slide, and you're probably glad for that. But hopefully the time was well spent because it preps us for all the others. But I do want to point one other thing out. Note that run 3, the dry scenario, which is the black dashed line, is actually too slow compared to observations. So actual discharge by this time was apparently wetter than this. And run 3 was dry enough, I guess, that the two issues I just mentioned were less of a factor. Now on slide 17, I'm showing predictions by April 2011, about 5 months since removal. Erosion in Simkins impoundment is still too complete, and so deposition in the Bloaty impoundment is still exaggerated. Also, there's deposition downstream at the fall zone for runs 1 and 2, considerable amounts of deposition. We know that no Simkins sediment was below Bloaty Reservoir at this time. Not just from the cross-section measurements, but we know that just visually in the field. It was obvious. It was all hung up behind the Bloaty Dam. Notice that the hindcast run, the black solid line, does better on this count. It's not showing material down below Bloaty Dam. And that's right. Run 3, the dry scenario, shows this too, but it remains too slow. It's still not eroding as much as we saw out of the Simkins impoundment at this time. By September 2011, about 9 to 10 months after removal, observations document sediment below Bloaty for the first time, and I'm pointing to those in Reach 3 on slide 18 right now. I'm circling them with my cursor. Tropical Storm Lee in early September 2011, which was an approximately 10-year event, eroded more sediment from the Simkins impoundment, and it also excavated Simkins sediment from the Bloaty impoundment, and it moved that material downstream for the first time. Runs 1, 2, and 4 show sediment downstream at this time too, so that's good. But they have it down to Reach 4 already, which is the fall zone. Note the observations don't show that. Instead, they show it in Zone 3. Runs 1 and 2, as you've seen, have been showing deposition at the fall zone for a while now, and now Run 4 does too. But all three are too fast. And notice that all three missed the Reach 3 deposition entirely. That's where the deposition was at this time. None of the model forecasts capture it, nor the hindcast. They're all predicting it down at the fall zone. Notice that Run 3, the dry scenario, misses all of this. It still shows no sediment downstream of Bloaty. So now I'm on slide 19, April 2012. It's a year and a half or so since dam removal, and observations now show sediment deposition in the fall zone. It's catching up to forecast model Runs 1, 2, and hindcast Run 4 that has recorded discharge. Notice that Run 4 does a little better than Runs 1 and 2, but it's still too fast. Run 3, the dry prediction, is still behind. It shows everything still hung up behind Bloaty, which isn't true. Erosion behind Simkins for every run but Run 3 is still too great at this time. Thus, deposition behind Bloaty is also too great. But there's an additional reason Bloaty pool deposition is exaggerated in the model at this time and the previous time horizons. And that's because active channel width in this area was overestimated from aerial photographs. This is that area where I pointed to earlier, where the pre-removal estimates from aerial photographs of channel width were out of step with the actual field measured values. This mistake in the input data causes the model to store too much sediment here. And it probably also partly explains why the observed deposition in Reach 3 is not captured by the model at this time horizon or the previous one. So now I'm showing a survey from a couple months later on slide 20 of just the DEM areas. And these are those areas of full bottom topography. And it pretty well demonstrates the overestimated erosion in the Simkins impoundment. And I'm circling that with my cursor. The overestimated deposition in the Bloaty pool and the fall zone further downstream. By November 2012, which is what I'm showing now on slide 21, which is 2 years since removal, observations show more deposition at the fall zone, in line with model predictions, which have been showing this for over a year. But there's still deposition in Reach 3 that's not captured by any run, although Run 3 actually shows a very small veneer. So maybe finally Run 3 is coming on. But nonetheless, the other models, and mostly model Run 3, are missing, again, this deposition in 3, but doing better down at the fall zone. Note that Run 4, actual discharge, is well in line with observations in the Bloaty impoundment at this time. So I'm pointing to the observations, the dots, and the Run 4 is pretty well in line with that. by November 2012. And I believe that's because run 4, actual discharge, is wetter than runs 1 and 2 and 3 by November 2012. So those runs still show too much sediment stored behind Bloaty Dam. And the survey of just DEM areas from a couple months later, which is slide 22, January 2013, shows a similar picture. Okay, so now I'm on slide 23, and I'm just going to sum up the validation results. The forecast had some limitations, and I've been emphasizing those as we looked at the plots. I've been emphasizing mostly where it hasn't performed very well. And one of those, obviously, is impoundment erosion was too fast and too complete. And so downstream deposition was too fast and thick in some areas. The second limitation was the input error that enhanced bloaty pool deposition. So the error in estimating channel widths that I just showed a few moments ago. And the fact that reach 3 deposition was mostly missed by all the forecast models and hindcast model 4. So those are the major limitations. But the forecast also got a lot right, especially for project planning purposes. And I haven't been emphasizing those, but I'm going to emphasize them now. They gave a reliable prediction of deposition pattern at a coarse spatial scale. They got that right. More specifically, they predicted the greatest deposition would occur between Simkins and Bloaty, and that was correct. Sediment deposition was predicted downstream of Bloaty to be less than 0.6 meters, and that was correct. And sediment deposition downstream of Bloaty was predicted to be persistent, and that proved to be correct with observation. Stakeholders involved in the planning process found the last two listed here particularly useful, giving kind of an upper limit on downstream deposition, especially near the fall zone, because that's where there's some, I should have mentioned that a lot of this site is in a state park, and in that area there's a lot of state park infrastructure, and so there was a lot of interest in how much deposition there would be magnitude-wise and how long would it stick around, those last two bullets. And the model got that pretty right. Okay, so let's now look at the hindcast results. We've already been looking at one of the hindcast runs, run 4, which improves the forecast model with observed discharge. Now we'll focus on the other two hindcast models, run 5, where we ran observed discharge, excuse me, I jumped the gun there, where we ran observed discharge and improved the input channel geometry, and run 6, where we did all of that and improved the estimate of the stored sediment volume behind Bloaty. So remember, run 4 is just observed discharge, run 5 has observed discharge and improved input channel geometry, and run 6 does all of that and improves the estimate of the stored sediment volume released from Simkins Dam. So this time we're going to move through the plots a little more quickly because the results are pretty similar to the forecast models. But we'll focus on 3 areas of improvement that the hindcast models offered. The first area of improvement the hindcasts offer is that none of them prematurely move sediment below Bloaty Dam. And that's because all of them use observed discharge. Remember that forecast runs 1 and 2 showed deposition below Bloaty as early as February 2011, which is the time period I'm showing here. And that's not the case with all of the hindcast runs, run 4, 6, and 5. So now on slide 26, I'm showing results for April 2011, and the hindcast models again properly show no deposition below Bloaty Dam. And I'll say again that forecast models runs 1 and 2 had substantial deposition at the fall zone by this time. The hindcast models properly do show sedimentation below Bloaty at September 2011, which is slide 27 that I'm showing now. So they're getting it right on the timing. September 2011 is also when we see the second improvement brought by the hindcast models. Runs 5 and 6 show deposition in reach 3. Remember, that was missed entirely by the forecast models in run 4. And as we know, the observations are showing that at this time, September 2011. The models aren't getting it perfectly, but again, the forecast models missed this altogether. Runs 5 and 6 capture deposition in reach 3 better than the forecast models and hindcast run 4 because of the improved channel geometry that they have. Specifically, they have improved representation of channel width in the Bloaty impoundment, a reduced width, and that means less sediment is stored there and instead moves downstream. An increased variability in bed elevation in reach 3 in these improved models results in greater deposition in those models in reach 3. And finally, I want to highlight how hindcast model run 6 improves on the sediment deposition estimates downstream of Bloaty at the fall zone. Remember, run 6 is using an improved estimate of how much comes out of the Simkins impoundment. And you can see that it does better than runs 4 and 5, which use the estimate that was 20% too large. It does better in the impoundment and especially down at the fall zone with observations. And I'm showing that again at June 2012 on slide 29 with the DEM only surveys. Better fidelity with run 6 with the actual DEM surveys down at the fall zone. Good fidelity in the Bloaty impoundment as well. And November 2012, run 6 is doing better than the other runs that time horizon as well. And finally, January 2013, it shows this same characteristic. That's on slide 31. So to sum up the hindcast model improvements then, there's no sediment below Bloaty before September 2011, and that's for all hindcast runs, and this comes from observed hydrology alone. There's improved modeling of deposition in reach 3 for runs 5 and 6, and this comes from improved channel geometry. And there's improved prediction of fall zone deposition for run 6, and this comes from an improved estimate of the stored sediment volume that was released from the Simkins impoundment. Okay, so then I'm now on slide 33 of 35. And so I'm going to kind of wrap things up here with a summary of the main points. As demonstrated with the Simkins forecast models, 1D forecast models can accurately predict deposition patterns at a reach scale, but they can't do so for sediment thickness or timing at finer spatial scales. And that's because they simplify complex 3D processes. There were two Simkins predictions that were most useful for stakeholders that were correct, and that was that deposition below Bloaty would be less than 0.6 meters and persistent. And despite modest improvements, conclusions made from the hindcast models with improved input data would have been comparable to those made from forecast models. So what I'm saying
Matt,
here at this point...
Matt, I'm sorry to interrupt you again, but your screen seems to have disappeared from my view, so I'm guessing us as well. Can you just make sure something on your network didn't kick you off and try to reshare your screen?
Yeah. When did you lose it?
Just now.
Oh, yeah, you know that little yellow box isn't showing. So yeah, I have to rejoin. I'm doing that right now.
Okay.
So it fell off at the beginning of the summary?
No, I think as you got through summary 2 is when it
Okay.
just fell away.
Too bad. I hit rejoin, but I'm not seeing anything happen. I wonder if I should. Are you seeing anything?
Not yet. Give me 1 second. Let me see if I can.
That's strange. I haven't lost internet or anything. I'm getting emails. You know what I'm going to do? The good thing is they're just text slides. I can just read them.
Sure.
So, but let me see if I can quickly get back in by just starting from the link again. It'll just take a minute, and we'll just see if that does it. Sorry, everybody. I don't know what happened because I have internet otherwise.
All right,
Short
well,
intermission.
why don't you just keep going with your conclusions, and we'll see if we can get you
Okay.
back up.
I'm back in, and if you can share, if you can, give me control, I can get everybody back.
Yep. Here you go.
Wow,
All right, you should be able to put your screen back up.
Okay. It's coming. You should be able to see it now. I have the yellow box back.
Yep, you're good to go.
Okay. So
We are
now
seeing your presenter mode.
right. I want to change that, but I can't get under there until that thing goes away. Okay. So you lost me where? Here?
Yes.
Okay. So point of summary, the correct Simkins predictions that were most useful for stakeholders were deposition below Bloaty would be less than 0.6 meters, and it would also be persistent. Project planners and others involved found those particularly useful. Despite modest improvements from the hindcast models, conclusions made from those models with improved input data would have been comparable to those made from forecast models. And what I'm saying with this point 3, which is exactly where we left off, is the hindcast got things a little better, but the areas of improvement wouldn't have affected project planning. For example, point number 2, they still show deposition less than 0.6 meters and persistent deposition. So some of the major conclusions that were most useful really weren't affected by the improvements brought by the hindcast models. So we continue to recommend simplified means for estimating input channel geometry, meaning measuring estimated widths of the channel from aerial photos, or using water surface elevations, or other available data for the long profile, rather than using detailed geometry. And that's for numbers 1 and 3 that I just presented. I'll click back to those. 1D forecast models really only accurately predict things at a reach scale, and because of that, when you get modest improvements with hindcast models, they're only so helpful. But maybe even more important, when you do this kind of modeling, you always have what's called a model zeroing or spin-up process, where the modeler actually has to change channel geometry so that the model can accurately simulate existing conditions. And so there's a question, even if you have really detailed input cross-sections or detailed long profiles, if the modeler is going to go and change those anyway in this zeroing or spin-up process, it raises a question along with the other two reasons I gave above as to whether or not the extra expenditure is worth it. Okay, and this is the last point here. 1D sediment transport models, as the one we just described here, can provide accurate, timely, and cost-effective predictions for project planning, or at least that's what we're putting forth here today and in the paper where we describe this study. So with that, I'll finish, and I see hopefully 10 minutes for questions.
Yeah, awesome. Thank you so much. We do already have 2 questions in the queue for you, so let's just jump right to it. First question that came up is, can you suggest potential causes of vertical degradation of the average bed elevation in reaches 3, 4, and 5?
I'm sorry, can you repeat it?
Can you suggest potential causes of vertical degradation of the average bed elevation in reaches 3, 4, and 5?
Oh, why there was some observations showing degradation?
Yeah, I believe that's what this is asking. Yes.
Yeah, I'll try to click back to that. That's generally natural degradation that we're picking up over time. So, for example, if we go back to the validation models and we go February 2011, there's degradation shown here in the fall zone. That's a fairly erodible reach, and we do pick that up. And because this is an average bed elevation that we actually derive from a total channel area, some of that can be associated with changes in width too.
Great. Another question, and if anybody else has a question, please get them typed into the chat box. There's one other question in there right now. It says, can you clarify what you mean by persistent? And that has to do with your summary slide. Item 2, period of time, and would you expect that to become permanent?
Yeah, that's a good question. So this time period I showed you was 2 years after removal. And so what you see is we start to see deposition at 2011 downstream, and really by 2012 it's pretty full on at the fall zone, and that hangs around for a while, and you can see that in the plots, and it continued to hang around for another couple of years. So when we say persistent, we mean it hangs around for a number of years. I think the model predicted it would be up to 5 to 6 years, and it was probably a little less than that in the observations. But I'm not showing that full time period here. I'm just showing the first couple of years.
Good. Another question, Ken. What was the level of effort in terms of hours for the modeling? And same question for the monitoring.
I can't really answer the first one just because I wasn't a modeler, so that's something Yantel would have to answer. For the monitoring, oh geez, in terms of hours, I guess that depends if you're talking just field hours versus analyses and whatnot. But just talking about field time, we have represented by this study, we had 6 field campaigns. And so, each field campaign was a few weeks. So I'm not going to add that up in my head and display my poor level of arithmetic, in public. But yeah, it's a fair amount of hours. It's like a month worth of field work, 6 times over. One of the areas that really took a lot of time was those detailed topography areas, the DEM areas.
Yeah. Okay. Another question. The model looks to spike between measured locations. Did you make observations in those locations?
Oh, just certain areas that are showing like higher accretion areas. Well, where we have coincident observations, we can do that. We were looking at more gross scale though, again, because it's a 1D model, and so we kind of generally tend to assess things on a reach scale. So like reach 4, for example, is the fall zone, and reach 3 is the Piedmont zone, and so forth. We don't get too hung up on particular fine spatial scale areas. I don't know if that's answering the question correctly, but.
Okay. There's not another question in, but I was wondering if you're applying this to the bloating removal as well, to see how that looks using some of the knowledge gained through this modeling exercise.
Yeah, that's a good question. We actually did a separate modeling prediction for the bloating removal, and we've had the monitoring ongoing as well. We have not gone back and done the same kind of validation study for that modeling exercise, although we could. And it's probably worthwhile because the bloating impoundment is a different animal. I didn't get into it in detail, but there we had as much as a third of the impoundment deposit was mud-sized sediment, so silt and clay.
Right. Okay. And I guess rolling into that, we got another question that came in about input and output of grain size distributions.
Yeah, we used grain size distributions that came from cores of the Simkins impoundment. So we had, a regular cumulative frequency distribution that we used.
Okay.
From field data.
All right, and we have one more in. Is it possible that the extended dry period allowed sediment to be stabilized by vegetation, reducing mobility at later high flows? And was vegetation monitored during post-removal surveys?
Yeah, good question. We did not do vegetation monitoring, but I just know anecdotally that didn't happen. Like we didn't get vegetated bars at the fall zone, for example. There's a number of reasons for that, but probably the best reason is there's been a pretty high frequency of floods in the post-removal period, including 2 very large floods. And so kind of nascent vegetation, stabilizing bars would not do well in those events.
Yeah. All right. Well, I think we're done with questions, and it's just about right on time as well. I don't see anything else coming in. So, Matt, thank you very much. We have recorded this, so we do have a new website for our committee, and we'll try to get this up there on that website. Thanks, everyone, for listening in. And Matt, are you open for additional follow-up questions if anybody has one?
Certainly. Yeah, they can send it to my email, and I'd be happy to correspond with them.
Okay, sounds great. Thanks again, Matt. Thank you, everyone, for attending.
Thank you. Appreciate the opportunity.